MDM4U 5.4, the binomial theorem. What we're going to be learning is a theorem that can help us expand binomials. So, a binomial is a polynomial expression with two terms. And to the power 0, anything to the power 0 with the exception of 0 to the 0 is equal to 1. A plus b to the 1 is just equal to whatever the base is. But a plus b squared, that's a plus b times a plus b. And what we can do is multiply this using distribution, a times a times b, then the next term, b times b, and collect like terms to get the following expression. Next, a plus b to the power 3, we could write this out as a plus b times a plus b plus a times a plus b. However, it's better to use recursion. The previous result, a squared plus 2ab plus b squared, can be written here because this is a plus b squared. That's equivalent. So just multiply it by one more power, a plus b. And this is the result when we use distribution of the first term and second term through the bracket to get this expression once we collect like terms. And remember, they're like terms when the exponent of each variable is exactly the same. Lastly, we'll use this expression as a plus b to the power 3 and just multiply that times a plus b. When we distribute each term in the first bracket through the second bracket and then b through the second bracket, we get the following expression, and we collect like terms and we get this result. Now, the numbers highlighted in blue, what are some things that we notice? So take a moment, you can pause and inspect. So one feature that might stand out is that the coefficients, the number out front of the variables, for each of these different terms in the expansion of the binomial are entries in Pascal's triangle. They correspond. Next, if we have to the power 0, we have one term. If we have to the power 1, we have two terms. With power 2, we have three terms, and so on. So, a plus b to the power n has n plus 1 terms in the expanded form. And as we discussed, the coefficients of the terms in the expansion of a plus b to the power n correspond to the terms in row n of Pascal's triangle. For example, to the power 4, this binomial has the coefficients in the fourth row, 1, 4, 6, 4, 1, in the expansion. So, what we've come to realize is that the terms in Pascal's triangle, each of these entries, correspond to combinations. So the Pascal's triangle equation, the equation that generates terms, for example, all that this is saying is that, for example, 1 plus 2 added together equals 3, and that's how we generate new terms in Pascal's triangle using recursion. Combinations can have the same property. So, applying this to Pascal's formula to combinations, 12 choose 8 is the same as the row before, one term before, as this mentions. So that will be 11 choose 7 plus the row before and same term, so that will be 11 8. And similarly, 19 choose 5 plus 19 choose 6. These two are two terms being added together, and they're consecutive. The position is one after the other. So this is going to be row 20 and position 6. That was given this side. We were able to look at the left-hand side. All right, so this binomial theorem, the binomial a plus b to the power n can be expanded using the following binomial expansion formula. So a plus b to the n, this is a general notation for any binomial, can be summarized using this combinatorial expression and used in sigma notation here. So that just means that we're going to have the row entries that are corresponding to Pascal's triangle, that's NCR. So notice we had NC0, NC1, NC2, all the way up until the final entry. And then A, that first term in the expression, is going to be raised to the power n minus r. And if we look at that in this expression, that is descending, meaning going down by 1 for each term. And then b to the power r, because of the nature of sigma notation, this is increasing by 1 at each stage, It starts off at 0, then 1, then 2, and is ascending, going up. So, that being said, we will always have the sum of the exponents to be equal to n for each of our terms. So this might be intimidating. Both this expression here using sigma notation and the expanded form on the right-hand side mean the exact same thing. So, a plus b to the power n. First of all, we'll establish that n, our degree, is 5. And what we will have is the coefficients will be 5, choose whatever we have for r, and then a to the power 5 minus r, b to the power r. And to be honest, you don't have to write out this expression in order to expand a binomial. This is just the shorthand algebraic way of this writing this expansion. So let's take a look at our first line. 5 choose 0 is the first term. We're going to substitute in 0, and that will be equal to 5 choose 0. Then we substitute in 0, a to the power 5 minus 0, b to the power 0. Therefore, what we will have is 5 choose 0, a to the 5, b to the 0. Let's take a step back and look at this entire expression. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. We've written out a row of Pascal's triangle. And then for our value of a, it's descending. So it starts off as a to the power 5, then a to the power 4, then 3, then 2, then 1, then 0. B is at the power 0, then 1, then 2, then 3, 4, 5. It's increasing or ascending. So that being said, we can't evaluate these any further other than the coefficient corresponds to Pascal's triangle. So that's going to be, we can evaluate this using a calculator, or if we have a reference for a Pascal's triangle handy, we would be able to just use those numbers in Pascal's triangle. Next, looking at values that are not just a plus b to the power 5. I can suggest that you become an expert with this expansion in general, with just a and b to the power n, so that the rest can be applied. We'll take a look at this right here. So this is the abbreviation using sigma notation for the following expansion. And we're trying to develop a method that will help us quickly expand binomials. So this isn't a necessary step to write in order to come up with the expansion of this binomial, but it is something that we can use for instructional purposes to check back to make sure that we're following along with the rules, so that as you're developing that skill, you can use this as a reference. So look at this right here. 4 choose 0 is going to be the first term, and then 2x to the power 4 minus 0. So that's going to be to the power 4. And as long as you remember that the first term starts off as the largest value to the power 4, and then the next term is going to be to the power 0, so it starts off at 0, the sum of the exponents will always be equal to 4. So we don't need to necessarily write something to the power 0. Next, we'll have 4 choose 1, term a, which is 2x in this case. A is to the 3, so b is to the power 1, because it must add to 4. So this is to the power 1. We don't have to write the exponent 1 because it's implied. Next, 4 choose 2 will be the coefficient. And it's helpful to use combinations when we can't see that Pascal's triangle directly with us. So that being said, 2x to the exponent 2, if r is 2, then the exponent for b must be 2. Notice that it goes 4, 3, 2, 1, 0 for our first term a, which is 2x in this case. And then our exponent for the b term is 0, 1, 2, 3, 4. It's increasing. But the sum of the exponents will always be equal to n, in this case 4. So in this next step, what we need to do is apply exponent laws and simplify where we can. 4 choose 0 is equal to 1. 4 choose 1 is equal to 4. Notice that in this stage, we can either use that calculator to evaluate those combinations or refer to a row of Pascal's triangle if that's available. Next, when we have a base to an exponent, we have to apply that exponent law to the term. So 2 to the power 4 is 2, 4, 8, 16. And x to the power 4. We have to apply our exponent laws in each case. Then, once we have applied our exponent laws, you need to write using only one coefficient in each term. So multiply 1 times 16, 4 times 8 times -1, 6 times 4 times 1, to generate each of these values in the final step to get one coefficient. Lastly, an exponent law that is helpful for this expression. This one's a little bit more complicated, but it's easier to understand when we have x plus 2 times x to the exponent -2 to the power 4. This is an equivalent expression. This is the negative exponent law being applied to this expression to simplify this last term. When we use negative exponents, we don't have to, we can take the reciprocal of the base and add a positive exponent, but it's easier to write in this form because it's all on one line. So we won't have to use fractional values. This is the abbreviation using sigma notation. Notice that n is 4, and our value for a is x, our value for b is 2x to the exponent -2. And we'll use the same process. We're going to use combinations as we go along, 4 choose 0, all the way up to 4 choose 4. Our first term, which is x in this case, will be to the highest exponent possible, so we'll start off at n and then decrease. Our exponent for b will start off with the lowest value, 0, and then increase. So this is that first line. X to the power 4, because 4 choose 0 is equal to 1. X to the power 4, because r, when 0 substitute, is 4. And then our sum of our exponents will always be equal to 4, so that would mean that our second term b, or 2x to the exponent -2, is to the power 0, which we don't need to write because anything to the power 0 is equal to 1. Similarly, for this right here, what I've done is evaluated the combination for each term as I went through to try to write this in less lines. It's a lot of terms in each expression, and if you can use sometimes less steps will reduce the opportunities for errors. Okay, so notice that the first term, a, has descending values or decreasing values for the exponent, 4, 3, 2, 1, 0. And the second term has increasing values. Starts off with 0, 1, 2, 3, and then 4. So we have to apply exponent laws to get our next line, and then simplify. So what we're going to learn lastly is the opposite process, where factoring using the binomial theorem. Determine the degree n. In the expansion of a plus b to the power n, there are n plus 1 terms. That we've established through our previous examples. Solve for a. The first term in the expansion of a plus b to the power n is a to the power n. So, that being said, let's just take a look at what that means by looking at these other examples. The first term in this expansion was x to the power 4. The first term in this expansion was 2x to the power 4. So that's 2x to the power 4. That would be 2, 4, 8, 16. And that's an error. Glad I caught it. Similarly here, a to the power 5 is the first expression here. So, lastly, b, if we're trying to write this in the short form, a plus b to the power n, the last term is b to the power n. And let's just confirm that by looking at previous examples. B to the power 5 is what we see for this expansion. This is going to be -1 to the power 4, which should be equal to +1. And similarly, let's look at the simplified version, or using the negative exponent. 2x to the -2 to the power 4 is going to be equal to 2, 4, 8, 16, x to the -8. So we can take advantage of that to try to factor an expression like this, a polynomial expression, if we know that it came from a binomial. So the first thing is establishing what is the value of n. If there's 1, 2, 3, 4, 5, 6 terms in the expansion, that means that n is equal to 5, because we always had that relationship that there are n plus 1 terms in the expansion. And that would mean that this is representing a to the 5. So a to the 5 is equal to 1. A is equal to the fifth root of 5. Solving using opposite operations, a to the exponent 5 is equal to the fifth root, which can be used with a radical notation, 5 root 1, or you could technically use a rational exponent where 5 is the denominator of the exponent. I like the radical notation. And the fifth root of 1 is positive 1. Similarly, our last term in this expansion is 32x to the power 10. And that represents b to the power, in this case, 5, because we established that n is 5. b to the power 5 is equal to 32x to the power 10. That's this term. So the same process, the fifth root. And in this case, it's helpful to remember the fifth root, we're going to have to do this in parts because this is a numerical value. 32, the fifth root of that is equal to 2. You might want to check on your calculator to make sure that you are capable of doing that calculation. Next, x to the power 10. As I mentioned, the rational exponent. This is like x to the 10 over 5, and that's the exponent is 10 over 5, which is equal to 2. So therefore, we have all the components of this factored form that we need. A is 1, b is 2x squared, n is 5. Okay?